So when you have an overload of negative on one side, you have an instantaneous positive negative, another one's doing the same thing, and then they'll latch on. But when those electrons move back, they fall apart. So it's back on, fall apart, back on, fall apart, back on, fall apart. It just is a constant back and forth motion. And you get a whole bunch of these doing this at the same time. When you have high temperatures, this will be impossible for them to form solids or liquids. So this has to be really low energy molecules in that they will slow down. When you decrease the temperature, the energy decreases, and therefore more likely to create these bonds, but they don't last very long even under those conditions. This is discovered by a scientist by the name of London. So we call these London dispersion forces. Don't even call them bonds because they're so weak. So this is a non-polar bond. This is the only non-polar bond that we deal with. Now, there is a bond that encompasses both this London dispersion forces and the dipole-dipole forces, which are weaker than the hydrogen forces. And sometimes it gets confused with London dispersion forces. The name for that are van der Waals forces. Now these are descriptions of weak forces, but it's because of this acknowledges the fact that there is a very brief positive negative charge or a very weak positive negative so-called charge in these molecules. This tends to cover both the London dispersion forces and it encompasses the dipole-dipole bonds. Boy, I got a lot of editing to do in this thing, don't I? Okay? So, now, let's take a look at some examples of this. We should be able to look at a molecule and be able to determine if it's polar or non-polar, and from that we need to write a potential Lewis dot structure for that, and then we can determine the type of bond, intermolecular bond. So let's take a look at CH3OH. Now right away we know it's polar. Why? Because of that oxygen. That oxygen tells you it's going to be a polar molecule. If we were to draw this out, and we've done this before, you have H here, H here, H here, and this is O and then H here. And actually I probably should put it at a 109.5 degree angle and show the negativity. But we do know that we got electrons here. This is the negative side here. That's going to be a weak positive part right here. And this is basically non-polar over here. So the interaction is going to take place right here. The fact that we have a hydrogen on the oxygen tells us that we are dealing with a hydrogen bond. Why? Because it is polar. Okay, another example. Hydrogen gas. Hydrogen gas is a single bonded hydrogen, hydrogen. Equal electronegativity. There is no more area, more positive negative, so we know that this is nonpolar. And the fact that this is nonpolar tells us that this is going to be London dispersion forces. Okay? So we have some practice problems for you to go through this. Have fun.